This video is an introduction to simple linear regression, and this marks a pretty big shift in the content of this course. Up until now, we've focused almost exclusively on scenarios with categorical explanatory variables, so comparing groups, whereas this week we're going to shift to scenarios with a quantitative explanatory variable. If we're using simple linear regression, this is for the situation where we have two quantitative variables. So both our explanatory variable and our response variable are both quantitative. That's when simple linear regression is appropriate. So specifically in this video, we're going to look at housing prices in Michigan, and we have a sample of 13 homes that were for sale just north of Lake Makatawa in Michigan, and we have the sale price and also the size of the house recorded in square feet. So first of all, let me just show you quickly how we would do this in JUMP. So we are talking about the relationship between two variables, so we're going to do analyze fit y by x, and we have a quantitative response, which is price, and a quantitative explanatory, which is size or square footage, and we'll click OK. So right now it's just showing us the scatter plot, the relationship between size and price, but if we click the little down arrow next to bivariate fit, there's an option to fit the line. So we're going to do that, and then this gives us all the output that we need. So using this, let's describe the relationship in terms of the form, the direction, and the strength. So for now, we can really just think of the form in terms of linear and nonlinear. Later, we'll talk about some different types of nonlinear relationships, but I think for this one, it seems reasonable to fit a line. If we just look at the points, a line seems like a reasonable representation of the trend. For the direction, we would call this a positive association, and that just means that as the house price increases, the price also tends to increase. So if they increase together, we call that a positive relationship. Notice that I have the word tends to in there because, of course, this is not a perfect relationship. There is some variability around the line, but there seems to be a clear tendency for price to increase with size, and that's not surprising. For describing the strength of the relationship, that's basically how far the points fall from the line. And there's a couple different ways that we can describe this. One is what we've talked about already. We can use R squared. So we can see our R squared here is 0.459. So we could say 45.9% of the variation in house prices is explained by the model using size. So this has the same interpretation no matter whether our explanatory variables are categorical or quantitative. We can also use the correlation coefficient to summarize the strength of the relationship. So the correlation coefficient is represented with a lowercase r, and it is just the square root of r squared. So in this case, we would take the square root of the decimal version, 0.4591, and that ends up giving us a correlation of 0.678. Notice here that it says the strength and direction of the relationship. So this could actually be positive or negative depending on the direction. So in this case, we've got a positive relationship, so it's just going to be positive, but sometimes you would have to add the negative sign there. By the way, in casual English, a lot of times people use the term correlation interchangeably with words like relationship or association, but you may have noticed I haven't actually used correlation much up until this point, and that's because in statistics, technically correlation is talking about the relationship between two quantitative variables, so we'll reserve the term correlation for this specific measurement of strength. So to illustrate this, I'm just going to use one of the applets from our textbook. So looking at this relationship, we have a correlation coefficient R of 0.83. If we square that, we get 68.2%. That's our R squared. And so this is sort of a medium amount of spread of the points around the line. If the points were more spread out around the line, they're not as tight around the regression line, now our correlation and our R squared are going to go down. So as the points get further from the line, the smaller our R squared and coefficient of determination would be. Whereas if the spread is really small, if the points are falling really close to the line, that means you've got like very accurate predictions based on that regression line. In that case, your correlation coefficient is going to get larger, and so will your R squared. Notice this is a positive relationship, but if I change this and make it a negative relationship, the correlation coefficient now is negative, but notice R squared is still positive because once you square it, you always get a positive number, and that makes sense with the interpretation. You can't have a negative amount of variability explained. Now let's look at the actual regression equation. So you notice that the equation is given here with the linear fit. So I've written the equation here as y hat equals b0 plus b1x. There's actually several different ways that you can write this, but it's important to know what y hat represents. This is the predicted value of y. So when we put a hat on it, that's saying that it's the predicted y as opposed to the actual data. And then x is just whatever we're plugging in. This is our explanatory variable. And the first number there, the number that's by itself, negative 59,368.7, that number is the y-intercept. So however you arrange the formula, the number, the coefficient that's by itself, that's going to be the y-intercept. And that represents the predicted value of y when x equals 0. So if our square footage was 0, then the predicted price would be $59,368.70. So we're using B0 to represent the intercept, and that negative number, negative 59,368.7, that would represent the predicted price. And it's important that we always say predicted because, again, this is not a perfect relationship. The predicted price of a house with 0 square feet. So hopefully you're noticing sort of two things that don't make sense here. One, to have a predicted price that's negative doesn't really make sense, but it also doesn't make sense to have a house with only 0 square feet, right? That's not really a house at that point. So sometimes the intercept is not going to have a meaningful interpretation depending on what your variable is. 0 may or may not be a reasonable value. And actually, even if it were, I would be nervous about making a conclusion here because if we look at the range of the data, there aren't any houses with less than maybe 900 square feet. So trying to extrapolate way down would be dangerous anyway. So we'll just put a little note here that the intercept is not always meaningful. And this is definitely one of those situations where it's not meaningful. And even if it were, 0 is way outside the range of the house sizes. And that's called extrapolation. We want to be really careful extrapolating beyond the data. So the intercept is the predicted value of y when x equals 0. To predict the house price for a different size, we would just be plugging into the regression equation. So if we wanted to predict the price for a house with 2,000 square feet, we've got our intercept plus the slope times 2,000. We're just plugging in our explanatory variable there, and that gives us the predicted price, $366,118. You can put that in here. And this is a linear relationship. We're assuming that the variables have a linear relationship. So that means that a 1 unit change in x always leads to the same change in predicted y. And the name for that rate of change is the slope. So this is the predicted change in y for a 1 unit change in x. So in this example, our slope is $212.74. So in context, we would say that as the house size, that's our explanatory variable, as house size increases by 1, and the unit here is square feet, so as it increases by 1 square foot, the predicted price, remember we want to say predicted price increases by this amount. So increases by $212.74. And units are important here. We want to make sure we've got the units for x and the units for y. So the fact that this is a linear relationship means that a 1 unit change has the same impact no matter where it is on the scale. So like if we go from 2,000 square feet to 2,001 square feet, our prediction is that price will increase by, rounding $213. And the same thing would be true if we went from 3,111 to 3,112. The model would predict that it was increasing by $213. So that's what we mean when we say it's a linear relationship, just that a 1 unit change in x always has the same impact on y, no matter where it is on the scale.